My name is Stamatis Alexandropoulos, and I will talk about the paper titled OVeNet Offset Vector Network for Semantic Segmentation. Let's start with a definition of semantic segmentation. Initially, we are given a set of classes, each of which is represented by discrete labels. For example, 0 corresponds to the road, 1 to the sidewalk, etc. Semantic segmentation is the problem of assigning a class label to each pixel. For the training and evaluation, we use the ground truth images, which are the correct predictions of the model. Below, we can see on the left the input image, on the right the prediction made by the model, and in the middle the ground truth image. As pointed by the arrow, the boundary pixels of such segments are misclassified. The aim of this paper is to tackle this problem of misclassified pixels, which leads to the major performance loss of the state-of-the-art models. This task has a wide variety of applications, including medicine, robotics, and autonomous vehicles. The base model of this project is the HRNet. HRNet maintains high-resolution representations throughout the whole process. As you can see below, it consists of parallel multi-resolution convolutions, repeated multi-resolution fusions at the end of each stage, and at the end, a representation head. Here, we can see a comparison of state-of-the-art models. HRNet achieves 80.4% mean AAU in Cityscapes, 75% in ACDC, and 44.6% in ADE20K. By adding OCR plus segments, it achieves better results. Transformers achieve the state-of-the-art results in the field. Now, we are going to talk about a new approach in this task based on offset vectors. We propose a method for improving class predictions by learning to selectively exploit informations from seed pixels. This is based on the following idea, which states that for every pixel P associated with a 2D semantically segmented image, there exists a seed pixel Q in the neighborhood of P, which shares the same prediction with the former. Based on the previous prior, we can solve the semantic segmentation task for P by identifying seed pixels Q. Thus, we let our network predict the offset vector O of P. As a result, we will design a new two-headed network. The first head of the network outputs the initial predictions of the model. Let's call them SI. The second head of the network outputs the offset vectors. Smaller vectors are lighter and color represents directions. By taking the SI predictions in the seed locations, we define a new prediction SS, S from seed. Sometimes the predictions might not be integer values, so we will use bilinear interpolations. Sometimes the prior is not always correct, and the initial semantic prediction SI may be referred to the seed-based one. Thus, the second head additionally predicts a confidence map, which represents the model confidence in adapting the predicted seed pixels. The class predictions from the two heads are fused adaptively using the learned confidence map as a fusion weight. In this way, we downweight the offset-based prediction and rely primarily on the basic one in regions where the prior is not always correct. As for the loss function, we have two losses. The first one is a weighted sum of the cross-entropy loss of each prediction. In this one, we introduce two hyperparameters, kappa and lambda, in order to adjust the contribution of each loss. As for the second one, we'll define a new loss for the confidence. This came by the idea that, given a pixel, its neighbor pixels must belong to the same class. So, the confidence value should be high for pixels whose offset vectors point to seed pixels that belong to the same class, and small for pixels that belong to a different class. The final loss is the sum of these two losses. To sum up, we design a two-head network. The first head is the semantic head, and the second one is the offset vector fields head. Semantic head outputs the losses, which are then passed through the softmax layer, and outputs the SI predictions. The offset vector field head consists of the offset vectors and the confidence map. The predicted offsets are used to resample the initial predictions, SI, and then they produce the prediction SS. These two predictions are adaptively fused using the confidence map, and we have the final prediction SF. For the training, we use the ground truth images. We designed 3 versions of the model. Every version depends on where the branch will occur. As for the experimental results, we'll use 3 datasets, the Cityscapes, ACDC and ADE20K. Cityscapes is larger than ACDC, both consist of 19 classes, and Cityscapes consists of images that are captured to good weather conditions, while ACDC in images captured in adverse weather conditions. ADE20K, on the other hand, is the largest of all. It consists of 150 classes, and it contains images from both indoor and outdoor scenes. As for the implementation details, following the same pattern with the initial model, both heads are initialized with pre-trained ImageNet weights. The total number of epochs is 484. The batch size is equal to 8, and after an ablation study, the kappa and lambda hyperparameters will be equal to 0.5. The pixel scaling of the offset vectors will be also equal to 0.5, and the branch will occur on the last stage. As for Cityscapes and the validation set, the initial model achieved 81.8% mean AU, while ours 82.4% mean AU. Below, you can see from left to the right the RGB images, the ground truth images, the offset vectors, confidence map, SI, SS, and SF predictions. As you can see in the red frame, SS predictions correct the false misclassified pixels made by initial SI prediction, and the final prediction SF is more accurate. On the test set, the initial HRNet achieves 80.4%, while ours 81.8%. We also tested our method in the HRNet+OCR model. This model achieves 81.9% mean AU, while ours built on it 82.4% mean AU. Here we can see some more qualitative results. For example, in the first row, we can see that our model tries to enlarge correctly the pavement in the red frame and reduce the terrain in the blue frame. As for ACDC, in the validation set, the initial model achieves 75.5% mean AU, while ours 75.91% mean AU. As you can see below, in the final prediction, our model reduces the erroneously misclassified pixels in the terrain and enlarges the pavement. And also, in the SS prediction, we can see some false pixels in the road. This specific part has high confidence in the SI prediction, so the final model doesn't have these misclassified pixels. In the test set, the initial model achieves 70.5% mean AU, while ours 73%. Here we can see some more qualitative results. In the first column, we can see that our model enlarges correctly the pavement and reduces the misclassified pixels in the terrain. In ADE20K, the initial model achieves 44.6% mean AU, while ours 45.3% mean AU. As a result, our method achieves better total results, better per class results, in similar training time, and it eliminates discontinuities and improves the shapes of the segments. Thank you very much for your attention.